Okay, this is the section 3.2, graphs of equation section. We're going to be learning how to graph things that are not just straight lines. We are going to spend a whole section on lines, that is going to be 3.3, and then we'll later on spend a whole sections on parabolas, which are x squared problems. But we want to kind of just have a general idea of what do you do if you have an equation you've never seen before? How would you think about finding that graph? So I'm just going to read through some of the notes. So two quantities are sometimes related by means of an equation or formula that involves two variables. We're going to talk about how to represent that geometrically. And the thing students don't always get when they are doing a graph is that you are actually showing a visual representation of all possible solutions to that equation. So every ordered pair that you draw as a point, or it's kind of as you connect the points, those ordered pairs even in between, that are on your specific curve or line, all of those points plug into the equation and make the left side equal the right side. So that's what we're really showing someone, is we're showing them all of the possible solutions. And when you do that, that's called the graph of the equation. Now, we don't ever get a perfectly exact graph unless we're dealing with usually lines and a ruler. When you're dealing with curves, you kind of get more of a sketch. A sketch is just where we find some points that we know work, specifically some key points, and then we just kind of see what the shape of that is. Now, most of the time, if your graph is very simple, you could do this by a table of values. And if you don't remember what a table of values is, it's just what we call an XY chart. You pick some x's, like -1, -2, blah, blah, blah. You plug them into an equation and you get a y. Now, for complicated equations, though, things that we're going to do mostly in Unit 3, you may not be able to get a good picture of what's going on there. And if they get more complicated as you get into higher level math, you really need calculus and some other computer graphics sometimes to get a good idea of the shape. So for us, we're going to stick with things that if we can't get the shape easily from a table of values, we'll give you some methods on how to graph it. So for complicated equations, there are going to be other things that we'll learn, okay? Now, this one is one that most people have seen before. This graph is a parabola, and the y-axis is considered the axis of the parabola. What that means is that this parabola has symmetry of some kind. Now, we'll talk more about symmetry in just a second. The lowest point of a parabola is called the vertex, and in this case, it's 0, -3. And this parabola, what we talk about parabolas, we'll talk about how they either open up or down. If it looks like a regular U, it opens up. If it's upside down, it opens down. So those are just some terminologies that are going to come back into play, especially when we get into section 3.6. That's where we'll spend some more time specifically on parabolas. Okay, so when I said plotting some points, I said one of the ways to graph is to find some key points. Specifically, where do you cross the x-axis or the y-axis? So remember, x-intercepts are things that have x, some number, and then comma 0. Whereas y-intercepts are always 0 and then some number for y. So if you're trying to find an x and y-intercept from an equation, you want to use this column over here. If you want to find the x-intercept, you let all the y's be 0, and then you solve for x. If you want to find the y-intercept, you let the x's be 0, and you solve for y. So that's kind of the gist of this part. And remember, each of them is an ordered pair. X-intercepts are also sometimes referred to as zeros of the graph, or root of an equation. So those are just synonymous names, but 0 and root can encompass things that are not real numbers as well, so we have to be careful there. Okay, another topic, like I said, we were going to come to is symmetry. So this is showing you that graphs can have symmetry, and lots of them can have symmetry, but there are 3 specific kinds that we care about. One symmetry is called y-axis symmetry. Notice that your graph is a reflection of itself across the y-axis. So notice the only thing that changes is that if this point was xy, you still have to be at the same height, but your x is now negative. So notice the x is changing signs when you match the 2 points. Another symmetry is x-axis symmetry. So notice this is reflecting over the x-axis. If you folded it along the x-axis, you would see a match there. Notice this time your x has to stay consistent, but your y changes signs. So that's a key thing about how that symmetry works. And then for the last type, it's called origin symmetry. Now, like I said, there are other symmetries out there. These are the only three we look for in this class. This says that wherever you're at on the first graph, if you flip it twice, so over the y-axis and over the x-axis, you get what's called origin symmetry, which means if we tried to draw the points and connect them, they would cross at the origin, the line would. So notice that not only did x and y up here both end up being positive, but in the reflected piece, they're both negative, so both of them change signs. Now on the test, the only thing you have to be able to do with symmetry is to look at a picture and tell me which of the three symmetries it has. It could have one or more than one or none of them, so you just have to make sure you know what the symmetries are supposed to look like. Now there's something in the homework where we actually make you test for symmetry without a picture, which means you have to test it algebraically, and that had to do with what I was talking about with the signs changing. So if you want to test for x-axis symmetry, you change the y's to negative y's. That's what happened in the picture. And then you work out the signs. So what I mean by that is if it's a negative y squared, you actually say what is negative y times negative y. And then for y-axis symmetry, so we'll do one or two of these in a minute, you change the x's to negative x's, and you see if the equation comes out the same after working out all the simplifying and combining like terms. For the origin symmetry, you have to replace both letters with negatives of themselves and then simplify. So that's kind of one of those things you have to kind of see it to see what they're talking about there. So we're going to do this first example. It says sketch the graph of the equation and label the x-intercepts, the y-intercepts, then use the test for symmetry to determine if it has x-axis, y-axis, or origin. And remember, there's also the case that it could have more than one of those or none. So we have to think of that as well. Now I know that most of you, especially on the pre-video that we did or not the pre-video, sorry, the pre-assessment we did on day 1, remembered how to graph a line using y equals mx plus b. But if you didn't remember that, remember you could always try an XY chart. The common 3 points that most people plug in, if it's a line, is -1, 0, and 1. If you have something that's not a line, which means it's not x to the first power, then you would want to maybe try more than 3 points, which I will show you when we get to B. So this is 3 times -1 and then plus 2, so that's -3 plus 2, which is -1. 3 times 0 plus 2, because notice we're plugging it in for the x, that's 0 plus 2, or just 2. 3 times 1 plus 2 is 3 plus 2, which is 5. So we go over here and we plot our points, -1, 1, 0, 2, and 1, 5. Now I'm going to try to draw a straight line here. That may be difficult. Maybe we can use a shape for this. Yeah, there we go. So I want my, and I'm kind of off-centered a little bit where I need to be, but I want my line to cross through those 3 points the best that I can make it do it with this. Obviously, if you're doing this at home, you would use a ruler. Okay, so then notice that I was asked to sketch it, which I already did, but then I was also asked to find some information. Now we already have the y-intercept. In fact, when we plugged in 0 here, we got that. So we know that the y-intercept is 0, 2. If you want to find the x-intercept, you plug in 0 for y, so you actually solve this the other way. So 0 equals 3x plus 2. So we'd subtract over 2 and divide by 3. So it looks like my x-intercept has a -2/3, comma 0. And if you look at my graph, that kind of makes sense. That's not quite -1, so -2/3 looks right. And then we need to test for the symmetries. So here's my x and y intercepts. So to test for the symmetries, here's how it works. You take this equation, and I always write which symmetry I'm testing for so I know what I'm doing. Y changes to -y when you're doing x-axis symmetry. So we write -y equals 3x plus 2. Now, you have to resolve this for positive y now. So if you divide everything by a negative, notice that this is not the original. So that means that this fails, which if you look at the picture, you can see this. If you fold this across the x-axis, you're going to have part of the line going this way and the other part's going to go this way. So that's not matching up. Then we need to test for y-axis symmetry, which means we let the x be a negative x. So go back to your equation. And then we just work out the sign here. So that would be negative 3x plus 2, which is also not the original. That means it fails this test. So that means this has no y-axis symmetry, which again makes sense. If you folded it over, you would need the graph to be going up like a V shape. And then the origin symmetry, which I already know this one doesn't have. The only way a line can have origin symmetry is if it actually crosses through the origin. But this one you change x to negative x and y to negative y. So this would be negative y equals 3 times negative x plus 2. I usually work out the multiplication first, and then because this is a negative, I need to turn it back into a positive y because that's what we have here. So if I divide everything by negative, it still messes up this guy. So not the original. So this one is, right, a fail there. This has none of the symmetries that we were looking for, which I can visually see that, and that's all you have to do on the test is to be able to visually see that, but that's what we're dealing with. Okay, let's look at B. So when I do these types, when I don't know that it's a line, when I choose how to do my table, I go ahead and force the intercepts to happen while I'm doing my table. What I mean by that is I'll plug in 0 here, but I'll also plug in 0 here. And if that gives me enough points, then I won't have to do anymore. So, and what I mean by that is if I have enough, and usually you'll get 3 points out of this, not always. If you don't get 3 points for a parabola, you need to reconsider the shape, getting the shape again. So for this one, and we may still need to get more information anyways, it just depends on what these points come out to. For this one, I'm going to plug in 0 for x first, which gives me negative 40 because everything that's got a 0 times it's going to be 0. Then I'm going to plug in 0 for the y. This is now a factoring problem, which means there's actually going to be 2 solutions. So that's why I'm going to add a second 0 here. So this would be x minus 8 and x plus 5, which means that I get 2 different x-intercepts of positive 8 and negative 5. So I don't obviously give myself enough room to plot this one on this graph. Let's change this to counting by negative 10s maybe. Negative 20, negative 30, negative 40, negative 50, which means I'll count this by the same thing. So 10, 20, 30, 40, and 50, just so we actually have. Now if you do something like this is fine if you leave this alone, as long as this is scaling by the same amount each time you have a mark. So I just changed this to counting by tens. So this would be 8, 0, so that's right here. Go ahead and put those x-intercepts down, and negative 5, 0. And then I have this point 0, negative 40. Now, I don't know if that's the lowest that that parabola ever gets, but let me share a little insight with you. If you have 2 numbers on your x-axis, the lowest point on that parabola should be it should happen at the midpoint between those 2. So this is why midpoint was important. And now we'll learn a formula for the vertex later, but right now we don't know that. We're just going to have to go off what we know. So this would be negative 5 plus 8 divided by 2, and 0 plus 0 divided by 2. That's going to be 3 over 2 and 0. So it looks like we're kind of at 1.5-ish. That's what this decimal here would be. So notice that's going to not be the actual point. That's just the halfway point between these 2 points. But if we plug this into, and I'm going to use a calculator, that's why we give you that opportunity to have one. We would do 3 divided by 2 squared, because we're plugging into this, minus 3 times, anytime I put in a fraction, I put it in parentheses, 3 divided by 2, and then minus 40. So negative 42.25. So that's a lower point right there. So right about there. So notice that I'm just going to connect this. This has that parabola shape. And hopefully you can draw better than I can with this pen. So we have this parabola type shape. Now, I'm not going to test this one for symmetry using the algebraic method because honestly we're not going to make you do that on the test. So what we're going to just do is talk through the 3 symmetries. For this one, notice that this is not folding over the x-axis because this is a curve and these are 2 straight lines. That doesn't match up. Over the y-axis, it's pretty close, but it's not exact because you remember your vertex is actually right here. So you're not quite matching up perfectly. And then it does not have origin symmetry as well. So this has none of the symmetries. And then we can write our x and y intercepts. So our y-intercept was 0, negative 40. And we had 2 x-intercepts, negative 5, 0, and 8, 0. Now by the time we actually take the exam, you'll know all the methods of how to graph a parabola, so we won't be making you do it by a table. If we want you to graph a parabola, we're going to want you to use the more sophisticated methods we teach you in 3.6. The whole idea of section 3.2 is just what would you do if you don't know the shape. All right, so let's look at this next one. It's also a parabola, except this one's going to have a nice feature. It is going to have a symmetry, so I want to show you what one looks like that has a symmetry. So again, I'll start off with a chart and I'll try to let 0 be my x and y intercepts so that I can find those. So if we plug in 0 for x, that's negative 0 plus 2, so that's just 2. If we plug in 0 for y, that's supposed to be a negative x squared plus 2. We would add the x squared over to get rid of it being negative, and then we could take the square root of both sides, but that requires us to write that plus or minus. So that means we do have 2 different x-intercepts again. So we need to figure out what square root of 2 is. It's like 1.4, yeah. So this is roughly negative 1.4 and 1.4. When we graph, we can estimate like that. So negative 1.4 is one x-intercept. The other one is positive 1.4, and we have 0, 2 as our y-intercept. Those points are not wanting to stay. There we go. Now notice, this one is centered at the actual y-axis. That's because we didn't have the x term in the middle. Now, and plus, another way to know that this is the vertex is that it's exactly halfway between those 2 x-intercepts. So I really don't need any other points to be able to graph this. That's what that parabola is going to look like. So this is 0, 2 for the y-intercept. And the x-intercepts are negative square root of 2, 0, and square root of 2, 0. So there's my intercepts. For the symmetry, this one has y-axis symmetry. It does not have x-axis symmetry because if you fold across the x-axis, they don't match up. It also does not have origin symmetry because here is a point. Let's just use the actual intercepts. This is square root of 2, 0, so that means 0's negative square root of 2 should also be on the graph, and 0 square root of negative 2 is like down here. So that doesn't have that all the signs change possibility. Plus, you can also just imagine folding it twice. It doesn't match up to itself. So I wanted to show you the algebraic test just for this part though. So to show you how this does actually have y-axis symmetry, what happens is, remember we make the x's into negative x's to see if it comes out the same. And the reason this comes out to the same equation is when you square a negative, it actually turns back into a positive, but this negative out front keeps coming down. So this is the same as original, which is why it passes that test. But again, on the exam, all you have to know is how to pick out which symmetry it has from the picture. All right, we have 3 more to do real quick. So this one's a little different because this time we have x equals instead of y equals. If that ever happens, then one approach is to, first of all, just see if you can find it using intercepts only. And you may need an extra y-intercept this time because y is the part being squared. We'll just have to see. But we can look at, if it doesn't give us enough points, we can look at finding more by either plugging, and in fact I would plug in y's because the x is by itself. So let's just try this first. If I make the x 0, notice I get this. That would mean add the 4 over, divide by 2, and I do have to take a square root here. So I do get plus or minus square root of 2. So this will be negative square root of 2, and I'll need to add another point for positive square root of 2. If I plug in 0 for y, notice this time that goes a lot quicker because you just get negative 4. And notice this is very similar to a parabola except it's y squared instead of x squared. What happens when you have a y squared and an x to the first is you get a parabola on its side. So here's negative 4. And then we have, remember this was 1.4-ish, so negative 1.4 and a positive 1.4. Get as close to those points as you can. And notice this is a parabola on its side. Okay? Excuse me. So if we want to write all of our things that we need, x-intercepts, negative 4, 0, just 1. Y-intercepts, 0, negative square root of 2, 0, square root of 2. And this one actually has x-axis symmetry from the picture. All right, let's look at this next one, y equals 1/2 x to the third. So I'm going to be doing an xy chart. Plug in 0 for x and then 0 for y. If I plug in 0 for x, I get 0 cubed, which is 0 times 1/2, which would still be 0. Which means I don't even need to do this one. If the origin comes out as one of your intercepts, it is also the other intercept. So that's not going to help me. So I need to plug in 2 other points at least. So maybe negative 2 and positive 2. I'm picking 2 because that's a 1/2 out there. I want something divisible by 2. So y equals 1/2 negative 2 cubed, which would be 1/2 of negative 8 or negative 4. And then 1/2 of 2 cubed is 1/2 of positive 8, which is positive 4. Notice right away, this is both positive and these are the same 2 numbers and are both negative. That's a good indication that we might have origin symmetry. So 0, 0, 2, 4, and negative 2, negative 4. Now if you drew this like this, you might think this is a line, which is why we are going to do another set of points. Let us do negative 1 and positive 1. I know that's going to give us some decimals, but it'll be okay. So this is 1/2 negative 1 cubed. Negative 1 cubed is negative 1, so that's just negative 1/2. I want to do more points because sometimes I said 3 points is not enough. This makes you think this is a straight line, and it's not. Straight lines have to be x to the first power. If we plug in positive 1, we get the same thing, but it's now positive 1/2. If we plot these, negative 1, 1/2, positive 1, 1/2, you now see that this is not straight. It curves down, and then it curves up. This is a cubic, okay? And cubics are kind of like parabolas that got confused. So half of it's up and half of it's down. So this is a new shape for us. X to the third has this specific shape. And then our final one. Sorry, the video is a little long, but we're kind of doing everything we would have done in class today. This is the square root of x minus 4. So the problem with this is that you can't just plug in any number you want to a square root because you might get imaginary numbers. When we think about square roots, we have to think about their domain. Their domain needs to be greater than or equal to 0. You can take the square root of 0, but as soon as you take the square root of -1, you've got an imaginary number. So if we set the inside greater than or equal to 0, we know what to start with in our chart. And by the way, I didn't write some stuff down here. Sorry, let me go back to this other one first. This had x-intercept and y-intercept of 0, 0. It's the same. And this one had origin symmetry because it is a double flip to make it match. Okay, back to this last one. So the reason I wanted to point this out is there's not going to be a y-intercept on this graph because you can't plug in 0. 0 minus 4 is -4. That means you're doing square root of -4. So just because something is an equation doesn't mean it has both intercepts. So I'm going to pick things greater than 4. So 5, 6, 7, 8. We may not use all these, we just want enough to get the shape. So square root of 4 minus 4 is square root of 0, which is 0. Square root of 5 minus 4 is square root of 1, which is 1. Now notice what I meant by I don't want to use all of them. That's square root of 2. I don't want to do that. That's a decimal. 7 minus 4 is square root of 3. Again, decimal. If I can, I try to get nice points. So this is square root of 4, which is 2. Now you're free to get the decimals, but I don't like plotting them. So this would be 4, 0, 5, 1, and 8, 2. So notice this is like a parabola, but it's on its side, and it only has half of the parabola. That is because when you solve something like example D right here, if I wanted to solve this for y, I would eventually have to take a square root. When you take a square root, you do a plus or minus. So notice that shape right there, down here, it's a positive square root. If you wanted the other half of this parabola, essentially, shape, you would need a negative in front of that square root, and that will give you the bottom half. So our square roots are also a brand new shape for us. Square roots have this half a parabola type shape. And then this would only have an x-intercept, no y-intercept because that would be imaginary if we tried to plug something that small in. And this has none of the symmetries because there's nothing to reflect any of the directions. So none for symmetries. All right, I know that was sort of long and you may have to watch it a couple times because I tried to go through it quickly to make it bearable. This is, so for today, for the missed section, you need to be watching 3.1, the final piece that I just posted, and 3.2 in its entirety, and then I'll have a little pre-video for 3.3. We were supposed to cover 3.3 today. I think that's a little bit too much to try to do all in one session. So what I'm going to do is push the quiz back to next week. So it was supposed to be our next class meeting, but we're going to push it back to next week on either Monday or Tuesday, depending on which class you're in. And then what we're going to do is take the time from the quiz to cover 3.3. So that's how we're going to play catch up. But I will post a little pre-video for 3.3 probably tomorrow or later tonight, just to remind you about some terminology. All right.